we're asked to find dy over dx when x equals -1, when y is 0. Is this the question? Am I correct?
Yes, ma'am.
Perfect, awesome. So now we will differentiate both sides. So I'm differentiating the left-hand side, and the right-hand side. I know it's 0, -5 prime is 0, but still I have to put the symbol on the other, at the end, not here. Okay, perfect. Can anyone help? Let's see what was difficult here. So can anyone differentiate 5x squared?
10x.
Very good, awesome. Can anyone differentiate this, but we have to identify what it is first? Because
7x times 1 plus 7y plus times 1.
okay, so the first function prime is 7 times the second function plus the first function is 7x times y prime. What is, which is?
1. Ow.
dx over dy.
You mean dy over dx, yes. Perfect. We reach this point, plus.
Y.
Yes?
dy over dx.
Yes. So some of you, thank you so much, some of you resist the concept of times the inner function prime. I know I sound like a broken record, I always do, but if you resist this, you will not get where we are going. So please understand this concept. Okay, we are here now, plus.
Times y.
One more time. Yes, times dy over dx. -5 prime.
Goes away.
Yes. 0 prime.
Goes away.
That's it. Awesome. Since we are asked to find dy over dx, we notice that dy over dx is present in 3 terms. Here, here, and here. These 3 terms have to stay on the left-hand side. These 2 terms will go to the other side. When I rewrite the whole thing, I factor out dy over dx from these pieces. From this, and I have a 7x. From this, and I have positive 12y. From this, and I have positive 16. These 2 go to the other side with a negative in front. This is just algebra. From here, there is no calculus. Let's see, look at this and just let me know if there is any question. Is this okay so far?
I guess I'm kind of stuck on how do we know what to put the 7x plus 12y plus 16 to the left of the problem?
These 3 terms have the variable.
Okay.
Because I circled it. So because they have the variable, they have to stay on one side together with the other ones that have the variable.
Okay.
These 2 don't have the variable because this is our variable. They have to move to the other side. Since they are positive, now they become negative on the other side. Is this okay?
Yes, ma'am.
Better? Moving on then, everyone? Perfect. So then I solve for dy over dx. There is a minus in front 10x plus 7y at the top, and these three terms together in the denominator. Only now I can say I'm ready to plug in x equals -1 and y equals 0. When y is 0, this disappears because it's y 0. This is -10 at the top. This is -7. 16 minus 7 is 9. Negative with negative, final answer 10/9. Is this okay?
Yes.
Other questions? Anything else that you may have encountered in Pearson, in anywhere? Anything else? If not, we'll continue with approximations. Anything else? Anyone? Okay, so page 3. So finally, let's discuss 3.6. This is another application of differentiation. So there are a few things in here. One, it's called differentials. Then we have linear approximation. Okay, so let's start with differentials. Okay. Let's suppose we have to manufacture a disk. And this is the radius of the disk. And let's say the radius should be 1 inch. But it's not. It has an error. So when we measure all these disks, it should have 1 inch in radius, 2 in diameter if you want. But instead, the actual radius, we made a mistake. We have made an error. The actual radius is 1.01. Now, because the radius is 1 inch, so it was supposed to be 1 inch, the area was supposed to be pi r squared. R squared is 1, so the area was supposed to be pi. This was supposed to be, of course, inches squared. But it's not. Why it's not? Because there is an error in the radius, there will be an error in the area. It snowballs on us, right? We made an error here that will trigger an error in the area. If we have a disk and it has a volume, it will trigger an error in the volume. So this minor error carries over into anything else about this circle. And I chose the area. So what would be the exact error? The exact error, it's called delta y. And we will determine it in a moment. This was just an example. And we have many examples. Okay, so the exact error will be called delta y. What will it equal to? I'm going to write it in a minute. I'm going to show you a graph. It will be easier to understand. What will be the approximate error? That will be called dy, not delta y. This is delta y, but dy. And this is also called the differential of y. So we have a lot of concepts or vocabulary concepts, if you want. Differential, derivative. It's a different story. So differential, of y. This is the approximate error in the function. If we consider the function to be the area, the exact area will be delta A. Approximate error will be dA. So this is the function. Okay, so let's illustrate and we'll move on because I need a relationship between these two. We want to express or find a relationship between the exact error created by this tiny error, the exact error in the function created by this tiny error in x, or the radius. Doesn't have to be the radius, it can be anything. And the approximate error created by the same tiny error in the independent variable. And we want to know what is the relationship here. I'm gonna come back to page 3. We want to know what type of relationship. It can be less than, it can be greater than, it can be approximately equal, it can be equal, it can be less than or equal to, it can be greater than or equal to. We're going to choose in here one of these symbols, only one. Okay? So we're going to come back and let's illustrate with a graph so that we understand what this equals to. Okay, so we're going to go back to a function, any function. This is my page 4. So let's say, ask any questions, please. So here's the function. This is our f of x. And here is our best friend, point P. And point P has coordinates x. Can anyone give us the coordinate of the y coordinate of P? So P is on this function and its x coordinate is just plain x. What will be the y coordinate?
Just y?
True. Perfect. What is the other way of saying y? Excellent. Thank you very much. If this is x, thank you so much. This must be f of x. If this is x1, this must be f of x1. If this is 5, this must be f of 5. If this is 10, this must be f of 10. Good, we established that. Of course, our second best friend is the tangent, right? The tangent at that point. That's our second best friend. This is the tangent at P. Okay? Our third best friend is a point Q. Q is very, very close to P. Very close. But I am zooming in, because if I put it here, where it should be, this is where Q is, very, very close to P, not P, very close to P. On this side or on that side, it doesn't matter. Then we're not going to see anything. So I'm going to put Q here. This is our Q. And Q has x plus dx. What is dx? So dx is the error in x. In this case, is 0.01. You can say, why are you using dx, not dr? Well, fine, I can use dr. dr equals 0.01 inches. In general, dx is the tiny error in x. In my silly example here, is 0.01 inches. Okay? So therefore, this distance is very small. Q is here. This is very small, is dx. But dx is also delta x, because this doesn't change. So it's always the same thing with delta x. So what's the difference? Well, when I talk about the exact error, I have to use delta. When I talk about the approximate error, I have to use d. But then if they are equal, what does it matter? If I use this forever or this forever, that's true, it doesn't. But we have to be consistent. When we use d delta y, when we talk about the exact error, I will use this notation for the minor error in x. When we approximate and we are discussing delta dy, then I have to use dr or dx because of consistency. But it doesn't matter. They are the same. Good. So now I have x for x plus dx. Can anyone give us the y coordinate of q? This is very similar to what we've done a long time ago with the rate of change, with the difference quotient. So what is the x coordinate? What is the x coordinate? I'm sorry, the y coordinate of q. Absolutely. F of x plus dx, also the same thing with f of x plus delta x. Awesome. Great job. Good. So then, now we are interested in this distance. This is exactly the exact distance. This is delta y, the exact error produced by this tiny error in x. So what is this piece? This minus this. It's this minus this. This is the exact error in the function triggered by the tiny error in x. Because remember, q is right here. So dx or delta x, same thing, they are tiny, small. So then delta y, which is the exact error, is this minus this. F of x plus delta x minus f of x. This is the formula for the exact difference. What will be here? It will be delta A is A of 1.01 minus A of 1. Good. Moving on, one more step here, and then we can look at problems. So, what I'm going to do now, I'm going to extend this vertical line through Q, and notice that I created a right triangle. Again, this is extremely small. Q is here. I'm zooming in tremendously so I can explain what we're doing. Okay. So, looking at this triangle, I'm going to take it from here because it's easier to explain. What do I know about this triangle? I know this piece as being dx. I don't know this piece. This is what I'm looking for. What is this? This one. I don't know this piece. I'm trying to find it. And now let's talk about this one. Okay. I know that this is the tangent at P. This is a right triangle. I know that this is the tangent at P. And I do know that the slope of this line, slope, is, can anyone tell us, what is the slope of this line? Remember, it is the tangent at P. We had these kind of exercises or problems in which we were given a function, we were given a point, and we were asked, find the equation of the tangent, find the slope of the tangent, and then the equation of the tangent line to the graph of this point. I only need now the slope of this line. Keeping in mind that x of P is x. Can anyone tell us what is the slope of this line at P? What does the slope of the tangent at P equal to? Anyone remembers? How did we find the slope of the tangent at P? At any point.